Hello. So this is the second presentation of the series on commutative geometry. We'll talk today about quantum isometries, quantum reflections. So we've seen last time that the idea was that we want to construct geometries coming from the free analogs of Rn and Cn, but these analogs don't exist. So that's why I have to go one level below Rn, Cn. Rather look at the basic objects which encode somehow the geometry of Rn and of Cn. And these are the sphere, the torus, unitary group, reflection group. So we've seen last time that we have free sphere and tori. Now it's time to talk about quantum groups and also start constructing the arrows between them. So that's the plan for today. Let's find this presentation first. So here we go. So quantum isometries and reflections. So we'll be doing this today. Okay, so as I was telling you, no free Rn, no free Cn. So that's why we have to look into these quadruplets. I mean, the most basic objects beside Rn, Cn themselves, which are the sphere, torus, unitary group, and reflections. And so far we have pairs, spheres, and tori. Just in the four cases, there are of course some other geometries. So what we're doing now in the beginning is to understand how these four main examples work. Real, complex, classical, and free. So we have four of them. We'll complete later with more geometries once we have the axiomatization. So today we're going to complete with pairs UK and also with some arrows. So you see there are four objects, so 12 arrows between them. We'll construct four of them. To be more precise, from S to T and from U to K is very simple. You just intersect with something. But we'll discuss the construction of these arrows from S to U and from T to K. That's basically taking the quantum isometry group. And we see actually in the free case, a new kind of phenomenon appears. It's very weird. So we'll have a weird thing to be fixed and we'll fix it in the end. So that's for today, and next time we'll construct the missing arrows and these four main cases, and also based on all this knowledge we'll axiomatize what means non-commutative geometry in general. I mean, such a quadruplet, what are the axioms to be imposed on STUK? So we want to construct UK distinct quantum groups. So first, a brief story of the quantum groups. So we're using the quantum groups of Voronovich. These are they were introduced 30 years ago by Voronovich, and with the extra axiom that the square of the antipode is the identity. So we'll need that in this case here. We'll talk later about twisting, Q deformations, other things. For the moment, we want to keep things very simple, so we won't have a twisting parameter. Well, you'll see at the end. Actually, there will be a twisting parameter, but it's going to be -1, so it will fit into this framework. The square is the identity. So, the Voronovich algebra, you just take a sister algebra with a matrix which is biunitary, meaning U transpose must be both unitaries, whose entries generate A such that these three formulas define morphism called delta epsilon S. In this case, we say that A is C of G with G a compact quantum group, and we also say that it's C star of gamma with gamma a discrete quantum group. So why all this? Because of the example. So let's take a compactly group, which means a subgroup of UN. Okay, this is something well known, right? Compactly groups are subgroups of UN, but let's just take a closed subgroup of UN without even knowing that. And C of G is of course the C star algebra. By Stone-Weierstrass is generated by these coordinate functions. The grouping of unitary matrices, of course, U is unitary, and same for the transpose, that's automatic, right? For usual matrices, if a matrix is unitary, the transpose is also unitary. So we're done with the first two lines here. And delta epsilon S, well, they simply come by transposing the multiplication unit and inverse map of G, right? So definitely, if you transpose multiplication unit inverse, you should get some maps like this. Delta from A to A tensor A and epsilon from A to C, and this from A to A actually. Here we don't need the opposite algebra. And the formulas, well, we just take the usual formulas from the matrices, and that's more or less each other tensor here. You see, that's the multiplication of matrices somehow. UVij is sum of uik vkj. That's where delta comes from. Same for epsilon. I mean, we have the identity here, of course. And the inverse of the unitary matrices is just the adjoint. So you transpose, you put a bar. So that's what we're doing with the antipode here. So these are our examples, and you can also prove conversely that any commutative Voronov algebra, you apply Gelfa and you have this morphism, you end up with a group. So you see, I mean, the commutative case, these are exactly the functions on compact Lie groups. So that's why in general we call it P of G or G compact quantum group. Now, there is also the second class of examples, which is dual somehow to this. If you take a finitely generated group gamma, generated by G1, Gn, C star of gamma with the matrix formed by the GIs, the generators on the diagonal. So let's see, are the axioms satisfied? C star algebra is diagonal made by unitary, so it's by unitary, entries generate, of course. And delta, you see here is diagonal, so this formula just means that delta GI is GI tensor GI. Yeah, of course it works, you have such a representation. Here epsilon G must be 1, so that's the trivial representation. S of G is G minus 1. That's not exactly a representation, but if you put the opposite algebra here, that's why opposite is there. It is a group representation, so that's just fine. So once again, here, well, you can prove something like the Voronov of algebra is so-called co-commutative. So the form C star of gamma, so in general, you can call it C star of gamma. And all this is, of course, supported by Pontryagin duality too. So if G happens to be an abelian group, we have indeed this C star of gamma, gamma big the dual. So yeah, that's the formalism. Now it's exactly what Voronov did in his paper Compact Matrix Pseudogroups, like 30-something years ago. But here you see square of the antipode identity is clearly an evolution. We won't need all these deformations. We'll only need them as q is minus 1, but at q is minus 1 they fit into this framework. So that's what we need. Maybe also another comment. So of course, G is a compact matrix quantum group, if you want to, or compact quantum Lie group. There are more general things which don't have kind of representation and dimensional. We won't need these things. Also, gamma obviously is finitely generated. That's somehow dual to the fact that G is matrix. So once again, there are more general formalisms for arbitrary discrete groups, discrete quantum groups, not necessarily finitely generated. Once again, we won't bother with that. So the reason why we won't bother with all these things for even locally compact is because we have problems to be solved, right? So I have these problems here, I want to axiomatize this, do this, so which is exactly the formalism which is good for our problems. We're not interested in abstract things, we have problems to be solved, so I want a powerful theory, and that's the most powerful one for solving these problems. Now, well, what are the tools now? So we'll first explain the tools, and then we'll get to examples of these things we're interested in, U and K quantum groups. So the tools, of course, you have delta epsilon s, and I was telling you that this, when AC of G would be a classical group, compact Lie group, these are the transpose of the multiplication unit inverse. So they satisfy some kind of co-associativity, commutality, co-inversality conditions, and here they are. Or just take the group axioms and transpose them. It's very simple. Now this is true for compact groups, but it's true in general because you verify these formulas. Let's go back to the previous slide. You see delta epsilon s are given on generators. Just verify them on generator. So by linearity continuity should be true in general. And of course, well, the square of the antipode is the identity. That's clear also on the coordinates, and I should have put it here, but not really, because in group theory that's not an axiom. This corresponds to the fact that G minus 1 to the minus 1 is G for a group element. So in group theory, at least mathematicians, yeah, they say that this is not an axiom because this follows from the other ones. In scope algebra, it's not an axiom because it doesn't follow, but yeah, I can put it as a remark after the theorem. So we'll have you use these 3-4 things. Now, well, should we start looking at examples with these tools? Surely not, because these tools are just at the level where you learn what a group is, and that you have a multiplication that you can always use in unit and the inverse. So won't get very far, so you have to do something, and that's representation theory. So, well, first, representation theory, and also these groups are compact in hard integration. So these two things are important. So for the hard integration, yeah, that's the formula. I mean, that's the definition, the left and right invariance of the hard integration. So you want to construct such a thing, and the idea is exactly as in a classical case. So in a classical case, how is it? You take an arbitrary measure on your group and you convolve it. The more you convolve, the more invariant it will be, and well, you have to take a zero limit for things to converge. That's your hard measure. Here we'll do exactly the same thing. So we take unital positive linear form. That's somehow integration with respect to an arbitrary measure. And you make this zero limits, convolution being defined like this in terms of delta. It converges and it has this property here. And in addition, importantly, for any co-representation V, co-representation means something exactly like U. The integral of the coefficients is exactly the projection onto the fixed points. So that's Voronovich. Co-representation, as I was saying, is exactly a biunitary matrix satisfying these conditions, exactly as for U. Now, the problem is that I should have put this before the slide, but not really, because you see, yeah, let's see what this slide says now, is that you have a Peter-Weil theory for co-representations. More precise, any of them decomposed as sum of irreducibles. The irreducibles appear inside of the tensor products of the fundamental one, with the remark that U doesn't commute to U bar, so have all kinds of tensor products between U and U bar, non-commuting. So these are indexed by colored integers. I mean, K can be something like white, black, black, white, etc. U to that thing is by definition U tensor U bar, tensor U, tensor U, etc. So U to the white is U, U to the black is U bar. That's the convention. Now, what else? A, so that's the dense subalgebra of smooth elements somehow. The one generated by the UIJs decomposes as a direct sum of spaces of coefficients of irreducibles. That's of course not an algebra isomorphism, right? When I is commutative, for instance, this is true. So it's not a sum, it's not matrix algebras, it's a co-algebra isomorphism. More precisely, a star co-algebra isomorphism, and the summands are orthogonal with respect to the integration, exactly as in the classical case. And finally, the character of the irreps. So the character just reduce trace, right? Form an orthonormal basis of a central. A central is the elements of A which are invariant under the flip. So we have hard Peter-Weil. Now, as you see, these things are somehow intertwined because related, because when you want to state Peter-Weil, here you have orthogonality, here you have orthonormal, so you need hard here. And, well, when doing hard, you need co-representations in order to construct them. I mean, this theorem is exactly like this. It's not two theorems. In order to prove that things converge and have this property and it's independent of phi, you need to check this. So it's a bit tricky. I mean, you have to develop at the same time somehow high integration and Peter-Weil theory. Start with a bit of Peter-Weil, do a bit of hard, another bit of Peter-Weil, another bit of hard, and you complete your Peter-Weil. So these two slides somehow are, if you look at Voronovich's paper and the other paper surveys, whatever lecture notes, they are very related things. So that's how the theory works. Finally, you can go even further, the Tanakian duality. So that's even one level up, these are while. So you see, given a Voronovich algebra, all that matters, let's go to the, to this slide. So the reducible up here inside these tensor powers of U. So all that matters are finally these tensor powers of U, how to decompose them. And particular interest are these home spaces, right? So they form a so-called Tanakian category, tensor star category. Conversely, now, given an abstract Tanakian category, you can always associate to it a Voronovich algebra. I mean, just take UIJs, and for any T in your category, you say that T must intertwine in the corresponding tensor powers. Now, the theorem, which is Tanakian duality, once again, Voronovich says that these operations are inverse to each other. So this is very powerful because well, in general, what you do with compact groups, you kind of want to do Lie algebras and classify Lie algebras, and then get back to the groups via exponentiation. Here we don't have geometry, so the only method is via representation theory. And this is somehow as powerful as Lie algebras because finally, quantum groups, Voronovich algebras are the same as this kind of guys, which are like something linear. Yeah, it's a bit like a Lie algebra, let's say. So it's powerful. And well, you can go one more level up. So we're trying to go as high as possible for all our problems to become easier afterwards. So a quantum group is called easy when this home space is the Tanakian category is spanned by partitions. I mean, it's the simplest possible thing. So that's the philosophy. So this Tanakian category should come from some kind of combinatorial objects, right? And by linearizing. And the simplest combinatorial objects are the set partitions, just dumb set partitions. You partition a set into subsets. And the linearizing operation is like this. To any partition, you associate this kind of map. It's just a sum. These are Kronecker symbols, depending on whether the indices fit or not. And as basic examples, O and UN are easy. That's exactly the Brouwer theorem. What we get here are the pairings, and the pairings which will match the colors for UN. That's exactly Brouwer. So finally, I think that's what we will need. So I have basic level in quantum groups delta epsilon s, then high representation theory, level 2. Tanaka is level 3, easiness is level 4. So now at level 4, normally we'll be able to solve our problems. So let's get into it. First, we need to construct unitary groups, UN plus, UN plus. So here's your definition. You just take the universal system algebra generated by UIJ such that, well, U is orthogonal, that's what's written here, and here U is biunitary. So why do we get Voronovich algebra with my construct delta epsilon s? So delta I must map UIJ into these guys here. But these guys form a matrix, and if it's biunitary or orthogonal, this matrix, it's very easy to check it's biunitary or orthogonal too. So I get my delta. My universality is same for epsilon, same for s. So it works. These are quantum groups. Now, there are many things that can be said about them. So this is old stuff due to Wang. But the most modern and simple thing is to say that they're easy. So here's the Brouwer theorem somehow extended. So I added also the classical ones because it's nice to have this diagram. So they're all easy. And the categories are follows: P2 matching P2. So calligraphic stands for matching. And that's Brouwer. And in the upper row, it's the same thing but with non-crossing partitions. So why is this true? Because the crossing AB is BA means AB is BA somehow. The fact that the crossing is in the category means AB in BA, and the passage from bottom to top is exactly by removing AB is BA, removing commutativity. So if you think in terms of Tanakian terms, easiness, this means to remove the crossing, so you get this. So we're done with the UN plus, UN plus. Now, well, let's understand reflections. And here it's a bit tricky because reflections, you have to understand permutations first, right? They're sign permutations somehow. So let's first understand permutations, quantum permutations. So we'll look at SN. Let's first look at SN. So look at it as an algebraic group. I mean, permuting the coordinate axis, right? Of our permutation matrices if you want. So these are the coordinates, with 0 or 1, right? And the point is that, of course, this commute, but we don't want commutativity. What are the other relations satisfied by them? Well, they're projections because it's 0 or 1. Also, if you take a permutation matrix, of course, the sum is 1 of these projections on each row, each column. So let's call matrix magic if it's made of projections summing 1 up to rows and columns, and define C of Sn plus in this way, just a universal algebra generated by entries of a magic matrix. So once again, as before, let's go before. You see, I mean, it's the same thing. If your matrix is magic, these three guys here are magic too, so I get my delta epsilon s. The axioms are satisfied. Now, what are the main properties of permutation and quantum permutations? Well, it's quite tricky. So first of all, at n to 3, these don't exist. I mean, the inclusion collapses. Sn included into Sn plus is an isomorphism. But at n greater than 4, they exist. Why? Because you can use a trick. I mean, you can concatenate two by two magics that just don't commute. That gives you the fact that S4 plus is not classical nor finite. And of course, if it's true for S4 plus, S5, 6, 7, etc. plus are also non-classical nor finite. Now, so the problem, once you see this, the item 1, which was in Bang's paper like 20 years ago, you start saying, well, what's S4 plus? And by doing some algebra, it's actually a twist of SO3. And you can prove it in general at n greater than 4 that Sn plus has the same fusion rules as SO3. So in particular, if you use well, Castagnet's ability to have an analog of that, you see that at n is 5 or more, not only it's not finite, but it's not co-amenable, Sn plus. It's really very strange. It's really big somehow. So these are somehow some preliminaries. And now the main result, which is really very nice, is that Sn and Sn plus are easy, coming respectively from all partitions, all non-crossing partitions. That's a continuation of these Brouwer things. And you can also prove that the main characters for Sn and Sn plus are Poisson in the larger limit. So this makes a link with free probability. We'll be back to this later. It's just a preview of things to be done later. So all this, yeah, so 1 is what I was telling you by hand somehow, there's a few tricks. 3 is Tanaka, it's a Brouwer type thing. And 2 is a mixture of ad hoc algebra and things coming from Tanaka. I mean, the fusion rules, SO3, you get it from here, from non-crossing. It's quite standard. Okay, so now we can go into reflections. This is the last thing we wanted. Well, that's your definition. I mean, it's a bit technical, but if you think of Hn and Kn, which are respectively these products, that's somehow the condition satisfied. So Hn is real, of course, you have to put this. Anyway, J square is magic because if you take a permutation matrix with signs plus minus 1, if you raise entries to the squares, it becomes a permutation matrix. And that's the reason. And same in the complex case. Once again, proof, very simple. And alternatively, well, you have this risk product decomposition. You can define them by using some kind of free risk product with Sn plus, but you need both in practice. So this is equivalent to this. We'll need both. Now, what can be said about these things? Once again, they are easy and they come from partitions with even blocks. Even means each block must have an even number of elements. So once again, partitions, matching, non-crossing matchings. Once again, Tanaka. Now, so we have, let's put things together now. So we have a total of eight quantum groups that we introduced, right? And groups. ON plus, UN plus, HN plus, KN plus. So if there are 8, we should draw a cube, right? And that's the cube. And the arrows are inclusions. And what can we say about this cube? For instance, all the upper objects appear as liberations of the lower objects. That's clear. And also importantly, for any face, you see the big thing. No, the small thing is the intersection of the two medium things. You see, I mean, for instance, if I intersect here, the face which is towards us, Hn plus and On, I get Hn. I mean, you just play with the relations, you get this for all six faces. This cube will appear many times in all. It's very interesting. So, yeah, what's the conclusion? So finally, getting back to the quadruplets. So I had these two quadruplets before, real and complex, and now we have also free real, free complex. And well, not only we have the quadruplets, but you see, for instance, the things on how many objects we have here, 16, right? So 8 of them are in the cube, and well, you can draw there a four-dimensional cube with all of them, but better. We don't have the techniques for drawing that in PDF. So the idea is that not only we constructed the quadruplets, but we understand a bit some relations between them. So anyway, our next task will be that of constructing arrows, right? So we want all these things. Here I just put some lines, but we want 12 arrows between these things, right? So what's the plan? So first of all, we have some clear arrows. So if you want to pass from S to T, you just intersect with a big torus. We already talked about it last time. And same, if you want to pass from U to K, you just intersect with Kn plus, because that's the cube business I was talking about here. You see, if I intersect with Kn plus, let's say Un, I get Kn, and so on. You get it from the cube. So this cube statement is exactly what we need. So I have these arrows here, S to T, U to K. Now let's try to construct these arrows from S to U and from T to K, because these are quite interesting, and we'll see the other constructions later. So the passage normally, how do you pass from the sphere to the unitary group? By taking, from a sphere to unitary group, you take the rotations, right? The same from the torus to the hyperoctahedral group, I mean, from the cube, once again, rotation. So let's talk about this, about isometries. So we use isometries in an algebraic geometry sense, I mean, not Riemannian or something, so not metric. So that's what we use in a classical case. Let's say we just take, everything is inside the sphere, so we just take a manifold or even a compact space, or not even compact, just a subspace of the sphere. That's the isometries which keep it invariant, form a group, of course. Of course, for the spheres, you get the orthogonal unitary groups. And for the cube torus, you get Hn, Kn, right? So with this, you would say, well, very good. I'll just replace here. I'll just put a quantum group, and should probably get On plus Hn plus, and it's clear, but it's not. So let's try to do this. So find first the free analog, quantum analog of this. So I take now an algebraic manifold inside the free complex sphere. And the claim is that there is an affine quantum isometric group of X, G plus of X. So action means, of course, we must have a coaction given -4. So is this true? In order for phi to exist for the coaction, you see these variables here, less than Zi. Well, must satisfy the same relation defining the manifold, right? X is algebraic manifold. This means it comes certain polynomial relations. So these variables must satisfy the same relations. That's the condition for acting. So well, you just take Pn plus and you mod out by all the relations coming from these. The fact that the Zi satisfy these polynomial relations, you get your G plus of X. So I have a definition, now let's compute. And good news is that, yeah, for the sphere it works. Out of our 4 spheres, we get the 4 orthogonal groups, and we should. Why is this clear? Well, it's not exactly clear. For the free spheres, it's clear because, I mean, you cannot have bigger things acting there, right? But in the classical case, it's not exactly obvious. So you must prove that there are no quantum group actions on the spheres. And Well, there's a simple trick by Bhumik and Goswami. I mean, that's you just write the formula of the coaction. The trick is to apply the antipode to it and somehow relabel the indices and compare with the original one process, and you get that things commute. So you get it. And by the way, there's a whole story here. So this is how many 10 years ago, Bhumik and Goswami, and in the meantime, there was this big conjecture that any compact, well, actually, manifold is a bit more complicated. It cannot have quantum isometries. That was proved. But it's Riemannian, so here we are fine. But most of their tricks apply. I mean, they're not that Riemannian what they're doing either. So Bhumik Goswami proved this for Riemannian isometry somehow, quantum, but exactly the same proof applies to the affine case. That's what I'm using here. So anyway, we're done. So going back to our plan, where was it? So we constructed the arrow from S to U. So now the problem left is to construct the arrow from T to K, knowing that it should be the same. And the problem is that it's not. So if you let me tell you in advance the results, so the isometries of the tori, you get this weird thing, some twists of N and UN here, the usual tori. So let me first tell you what these twists are, and then we'll see this, and then we'll see the fix. So, how to twist? Well, there are many methods for twisting. So first of all, you would like to say, you take like a kind of Drinfeld-Jimbo thing from Q is 1, twist it to Q minus 1, but this is not good because when they do Drinfeld-Jimbo is not semi-simple. At Q is minus 1, we want semi-simple thing. So that's a wrong twist. Then you have all these cocycle twists. It's possible to do it with cocycles, but in our case, the columns are just easy, so we'll do a sure while twisting, I mean, based on easiness. So the idea is that I take an arbitrary easy quantum group, but actually I have to assume that it contains Hn. Normally the easy quantum groups contain Sn, but must assume this because I want the category of partition if you want to have even blocks everywhere, because I want a signature, and the signature is only defined on partitions with even blocks. So anyway, under a mild assumption, well, the twist is given by the same formula as before, so it's just partitions, but the implementation of the partitions is different. So the Kronecker symbols are now signs. They take values -1, 0, 1, with the signature of a certain of this Ij coming in. So it might just seem a bit complicated maybe at the first time, but extremely powerful because this gives you also the representations here of everything of the twist if you twist in this way. So you can see right away that many things, that G is amenable if and only if G bar is, and fusion rules, Weingarten integration, it's something extremely powerful, okay? So it might take a whole slide to present, but it's extremely powerful. You get everything you want with this. It's a kind of Q easiness at Q is -1. So this definition now, that's our computation, which is quite bad because we don't know what to do. So computation is the same as just use the same old trick of Bhumik and Goswami, you get this. So the problem is now, what's the fix with this? How can we pass now from the classical tori to the usual HNKN? Well, and the answer is that you have to intersect with Kn plus, right? So if you intersect, what happens is, you see in the upper row, nothing will change. In the lower row, you have to intersect some twists with Kn plus, and the idea is that twists somehow correspond to anti-commutation, and commutation and anti-commutation somehow corresponds to vanishing. So that's why the off thing, the continuous part vanishes. You're left somehow the discrete structure of your quantum group, which is HNKN. Well, that's philosophical. I mean, in practice, it's a few half a page computation. So you see, that's the fix. I mean, the passage from tori to reflection groups, it's not the quantum isometry group, but rather the quantum reflection group. You see, this thing, you can call it the quantum reflection group. So, very good. So as a conclusion now, we have With respect to last time, we advanced a lot. So last time we were having only, well, so first the classical case, and in the free case we're having the spheres and orthogonal unitary groups. Now we have also the tori, and then we're having the spheres and tori, sorry. Now we came up with these quantum groups, and also we have arrows like these 4 arrows. And well, what's left is to construct, of course, the missing arrows. There are like 8 of them, and then to axiomatize what we found. For the missing arrows, there are actually 2 tricks, two things which are subtle. So this was the first thing. When you see this, you say, wow, I won't be able to do this. And you see here, you don't even have arrows between this 1 minus 1 h and plus is totally not functorial. I mean, this iso construction destroys the functoriality. It's very bad. But the trick is to take reflections. So that was the first subtle thing, and we'll see next time that there is one more subtle thing, which is that's the passage from the torus to the unitary group. Actually, in the classical case, that's not clear either. So I was saying in my first lecture that well, the torus is the maximal torus of the unitary group, so you can reconstruct the unitary group, but that's of course very tricky. You have to know a lot. In the quantum case, it's even more complicated. So we'll see that there are there's a solution there. But for the rest, the other arrows, there are many of them, but they won't be that complicated to construct. So in short, that's going to be the idea for the next time. We did the hard part. Is just one more thing to discuss, one more technical issue, the passage from the torus to the unitary group. And then all this, we'll construct all the missing arrows, we'll put everything in a table, like we'll say that on commutative geometry is something coming from a quadruplet STUK, satisfying having correspondences between them. And with that, then we'll classify the geometries and talk also about the relation with coordinate CG. Okay, so that was it. So see you soon for another lecture.